In this lecture, we're going to talk about a special continuous distribution called the normal distribution or the Gaussian distribution. It probably looks very familiar to you since it is what most people refer to as the bell curve, and you've probably seen this in school where bell curves are used to shift marks up or down based on how well students perform. So this formula you see here is the PDF of the Gaussian distribution. Notice how they also use the little f notation on Wikipedia. The interesting thing about the Gaussian distribution, so we talked about last time that the mean and the variance are two special numbers that help us describe what a continuous distribution looks like. With the Gaussian distribution, the mean and the variance completely describe the shape of the distribution. So the mean tells us where the center peak is of the bell curve, and the variance tells us how much that bell curve is spread out. So you can see this yellow curve is very spread out, and the blue curve is spread out not that much. So let's talk a little bit about this formula. First, there's a normalizing constant. It's 1 over the square root of 2 pi times sigma, which is the variance. Actually, sigma stands for the standard deviation. Usually it's written as 1 over the square root of 2 pi sigma squared, where sigma squared goes inside the square root. So sigma squared is the variance and sigma is the standard deviation. Second part of the PDF is this exponential. So we take the negative of x minus the mean, which we denote by mu, square that, divided by 2 sigma squared, or 2 times the variance, and then we exponentiate that. Note that since we square the thing where x is, this PDF is symmetric. So if you go a distance from the mean to the left, or that same distance to the right, you will get the same value for the PDF. So let's do an exercise where we plot the values of a Gaussian curve from, say, minus 100 to 100. So we'll create a new function, call it myGaussian. We'll take in 2 parameters, mu and sigma squared, and we'll output an array. So n will be the number of different values between min x and max x. So we're going to start our little x value at min x, and then we want to know how much to increment x on each iteration of the loop. So we'll call that dx, and we'll say it's max x minus min x divided by n. So at the end of the loop, we're going to add dx to x. We're going to call this f. Okay, so we're going to return let's return the array of x values also. So x of I is going to equal 2x, and f of I is going to equal 2. So return x and f. So 1 over the square root of 2 pi sigma squared times exponential of negative x minus the mean squared divided by 2 times sigma squared. So let's do this for mu equals 0, sigma squared equals 1. Let's say minus 10 to 10, and then have 1,000 values between them. Okay, so now we can plot x and f. Alright, so we get this bell curve. So the peak is at 0 because that's the mean, and then it's spread out and from about -2 to 2. So the drop off, or how fast f of x goes to 0, is pretty quick. You can see the maximum value is about 0.4. Let's try that again with a smaller variance and some smaller values also of min x and max x. So let's do 0.1 for the sigma squared. Let's plot it again. Alright, so the drop off is even quicker now, where we get to about 0 at -1 and 1. And notice the peak value is above 1.2, so since this is a PDF, values above 1 are allowed.